Algebra II 7.10c, we're going to talk about first degree equations with complex numbers, solutions, and I've got a couple of theorems for you. So again, now we have 11 previous videos for complex numbers and imaginary I. If you haven't seen them or you become lost during this video, you can click on the description to watch them to catch up. So remember from chapter 5, the degree of a term is the sum of the exponents of the variables. And the degree of a polynomial is the highest degree of its terms. That was video 5.1a, and there's a link to that one in here too. Just look in the description. First degree equations in complex numbers are solved a lot like first degree equations in real numbers. We start by getting all the x terms to one side of the equation, like we always do. So that's what we're going to do here. We're going to start by getting all the x terms to one side. So we have 3ix plus 4 minus 5i equals 1 plus I times x plus 2i. So we're going to do adding a negative 4 and a positive 5i to isolate and get rid of this, all right, to eliminate this as an additive inverse. So we're going to put it on this side also because we have to do the same thing on each side of the equation. So now on this side we just have 3ix because that got eliminated. And on this side we have 1 plus I times x minus 4 plus 7i. See? Now we need to get this x over here. So we're going to subtract negative 1 plus I times x from each side. And we're going to get 3ix minus 1 plus I times x on this side and negative 4 plus 7i on that side. In fact, my parentheses was supposed to be on the inside, wasn't it? Like that. Okay, so this is a subtraction problem. We have 3ix minus 1 plus I times x. So if we distribute this, 1 times x is x, it's 1x, and 1i times x is ix. So really what we've got, because there's no x value on this side by the 3ix, we can say 0x plus 3ix minus 1x plus ix. If we stack this one on top of that one and put a 0 for the x value, and you can see we would get a negative 1x plus 2ix. There's an x here and an x here. So what we can do is we can set it on the outside of the parentheses because it could be distributed back in, couldn't it? So we can pull it out and put it out here like that. So we have negative 1 plus 2i times x. See? Instead of having to write both x's, we just put it on the outside with parentheses. Now we need to isolate that x by itself. And we divide both sides by this negative 1 plus 2i so that we make a giant 1 right here. And it's on this side also. We have to divide both sides. That isolates that x by itself. So now we just have x equals negative 4 plus 7i divided by negative 1 plus 2i. Okay? Now, if you saw video 7.9d about conjugates, we're going to divide by multiplying by that conjugate. So this ends up becoming a negative 1 minus 2i over negative 1 minus 2i for our value of 1. That's going to be our 1 right here. And we can FOIL this, can't we? We FOIL the top, we FOIL the bottom, and we get 4 plus positive 8i minus 7i minus 14i squared for the last ones. And we do the denominator and we get a positive 1, positive 2i, negative 2i, and negative 4i squared. Okay? We know these I squareds mean negative 1, don't they? So we're going to be able to multiply this back end by negative 1, aren't we? We can combine like terms. This positive 8i and this negative 7i make just an I with our buddy the invisible 1. It's just a 1i. And this is going to be multiplied by a negative 1, isn't it? So negative 14 times negative 1 makes a positive 14. And this negative 4 is multiplied by a negative 1. So that's going to make a positive 4. So now we've got 4 plus I plus 14, so that's going to give us 18 plus I on the top, and 1 plus 4 for our denominator, we can split it apart as x equals 18/5 plus 1/5 I, because there's that invisible 1 in front of the I, isn't there? So that'll be our numerator next to the I. See? So, linear equations always have solutions, and complex numbers were invented so certain other equations would have solutions. The number of solutions that a polynomial is going to have depends upon this very important theorem. Every polynomial with complex coefficients and of degree n, where that n is larger than a 1, okay? No zeros, no negative numbers. When it's larger than a 1, it can be factored into that many n linear factors. So if it's degree 2, there's 2 linear factors. See? The factors of a polynomial are not always easy to find, but they exist. So we can show that x plus I times x minus I is a factorization of x squared plus 1. When we FOIL this, we get x squared minus ix, back here, plus ix minus I squared. See? And these two middle ones cancel each other out as additive inverses, don't they? So we just have x squared minus I squared. We know I squared means -1. And when we distribute that negative, we get a positive 1, so x squared plus 1. So see? It worked. And this helps us answer the question about the number of solutions of polynomial equations. So here's our second theorem. Every polynomial of degree n, where n is greater than or equal to a 1, with complex coefficients, very important, with complex coefficients, has at least one solution, and at most n solutions, because that's the degree n, in the system of complex numbers. Now this can be confusing. So basically, if we have a polynomial equation with degree n, that polynomial is either of degree 1, which means there's a solution, or it means it can be factored into n linear factors. And they'll have at least one solution, but not more than n solutions. So if we have x squared, well, that's to the second degree, isn't it? Well, this polynomial has only one solution, but must be factored into 2 linear factors because it's got that 2 there. See? That's all it's saying. If it's to degree n, then it's got n linear factors. See that? It's degree 2, so it's got 2 linear factors, see? And at least one solution. So if a polynomial equation of degree n, it'll have n linear factors, and a polynomial equation of degree n doesn't have to have n solutions, okay? It may only have one, all right? Our next video is 7.10d. We're going to find square roots of complex numbers. I'm going to add this video to the Algebra II playlist. There's going to be a link to chapter 11 from last year where we talked about radical expressions, if that's where you're at. There's 11 previous videos for imaginary number I and complex numbers, starting at 7.7a, and all the links are in this description. I know that this is really confusing with those theorems, but if you could follow this, and if you have to watch this second half of the video again to look at that, that's okay. It's a lot better than going and continuing on confused, right? So keep trying. I know it's going to be tough, but you're gonna make it. I believe in you, okay? Bye.